In this video, we're going to introduce the concept of a derivative. So before we do that, let's review that average rate of change is the same as the slope of the secant line. So the slope formula, change in y over the change in x, is what we've been doing since middle school. A secant line connects 2 points on a graph. So here this blue line is a secant line because it connects 2 points on the graph of the curved function. Now we're going to extend that to talk about a tangent line. So if you remember from geometry, we looked at lines that were tangent to a circle. That means they touch the circle only once in this interval. And they never touch again in that interval. They may touch later, but not really close. So I'll kind of show you what that would look like for a function here in a second. Also remember from a prior video that if we wanted to find the slope between 2 points in function notation, you can see from the graph here, we have these two ordered pairs. And if you use the slope formula, which is the change in y over the change in x, we can take one y value and subtract the other. We could also take our x values and subtract them. And what we ended up getting was x plus delta x minus x. But since we can combine like terms, those canceled out. And we're left with this big ugly version of just the slope formula. So that's how we find the slope between 2 points in a secant line. And what we're going to do is we're going to turn that into something that would find the slope of a tangent line at 1 point rather than 2 points. So what a derivative is the slope of the tangent line at any one given point. Secant is through 2 points, tangent is through 1 point. And the derivative gives us the slope of that line. So let's go to a graph here. And I have the slope of the green line. I'll go ahead and box it in green. The slope of the green line in green. And then we have the slope of the red line at 3. So this is the derivative. And then I marked the distance between my two x values as delta x. And that's given there by h. Okay? So we know how to find the slope between 2 points. Okay? We do the change in y over the change in x. What we're going to be doing when we turn it into a tangent is we're going to take 1 point, in this case our green point, and we're going to pull it closer and closer and closer to the purple. And as we do that, you can see the slope in the green box is changing. And eventually these points get so close they turn into a tangent line. And so you can see what's happening here is delta x is approaching 0. The distance between these 2 points is getting smaller and smaller and smaller. It cannot actually equal 0 because when we calculate slope, we do the change in y over the change in x, and we can't divide by 0. So we have to use the concept of a limit, and we have to say what's happening as the distance between the 2 points gets really close to 0. So we go back to this green point, let's pull it closer and closer and closer, and you can see that it actually becomes very, very close to the exact slope at that one moment in time. Okay? So the green line is a really good example of what a tangent line looks like. So if we move that around, you can see that the red function has an infinite amount of tangent lines because every time we move to a different x value, we have a new tangent line. And the derivative of a function gives me the slope of any of these green tangent lines. So if we go back to our notes, we can see the definition of the derivative is here in this box. So all it does is it takes the slope formula between 2 points, and it says, what if we take those 2 points and we put them closer and closer together so that they become 0 units apart. And once we find that, we have the derivative. So our notation for derivative is very important. When you find a derivative, you must label it. We use f prime of x and y prime most commonly. We will use dy over dx specifically in a certain chapter, but all of these are ways to say the derivative. This guy is the most descriptive. It's read as the derivative of y with respect to x. These ones are not very common. So let's talk about some review real quick. So just as a reminder for function notation, if it said find f of 3, that means take the function f and plug in 3 for the unknown. So in this case, we have unknown in x squared and an unknown here in 3x. And all I've done is I've copied this function right here, but instead of x, I've left blank spaces. So what we're doing with function notation is whatever they're asking me to plug in, we're replacing in these blank spots. So I plug in 3 and 3, and if I simplify, I have found f of 3. If I use that same template for example B, this says now plug in h. So I plug in h into every unknown. I can extend that even further to a binomial. Example C is exactly the same, other than now they're asking me to plug a binomial in for each unknown. And the final example in function notation is what we're actually going to have to do in the definition of the derivative. We're actually going to have to plug in x plus delta x. So we take our function, again, imagine it's like a template, and for each unknown, for each x, we replace it with x plus delta x. And then we're going to solve. And one of those steps in solving usually involves squaring a binomial. So when we square a binomial, remember that means I'm going to take x plus 4 times itself twice. I would have to FOIL, and I would have to combine my terms. A shortcut for doing that would be something that you learned in probably 7th or 8th grade. It's not very common, so you probably don't remember, but we use it a lot, so it might be worth memorizing. So if we look at this problem, the shortcut says, let's go ahead and do this with f. The shortcut says, let's square the first guy, so we get 9x squared. We're going to square the second guy, so we get 64. And the way we come up with the middle term is we multiply the two together, and we always double it, so that we would get negative 48x. And that's just a little shortcut. This is what we would get if we FOILed the binomial and distributed. So let's go ahead now and apply our knowledge to an example. So the problem says find the derivative. Well, when we do that, we have to use this definition. The first thing we need to find is f of x plus delta x. So this says take my function, and instead of x, we're going to replace it with x plus delta x. So here instead of x, we're going to have x plus delta x. It's going to be squared, and then we're going to add 1. The next part says now we're going to subtract the entire function. So we're going to subtract the entire original function, and it's all divided by delta x. Now we're doing all of this so that we can find the limit as delta x approaches 0. That requires direct substitution, and when we try that, we get 0 over 0, which means do more work. We're going to try to factor out a delta x so that we can end up dividing by delta x. In order to do that, though, we need to simplify this. So first, we're going to square this binomial. We're going to use the shortcut. We're going to square the first guy. We're going to square the last term. We're going to multiply the two together, and then we're going to double that. So the center will get 2x delta x. And don't forget, we still have plus 1. And then we still have minus x squared, and we still have minus 1. If we continue to simplify, we see that x squareds cancel, the 1's cancel, and we're left with 2x delta x plus delta x squared, all divided by delta x. Remember, the goal is to plug in 0 for delta x, and we still can't do that. So we hope we can factor 1 out of the numerator. So we're going to factor out a delta x. Here we're left with 2x. Here we're left with 1 more delta x. In the denominator, we have delta x. And the reason we did all that is so we can divide delta x and delta x. So we really need to find the limit as delta x approaches 0 of 2x plus delta x. Now we can use direct substitution. We plug that in and we get 2x. This is the derivative of the original function. And then just a couple other things. If it's differentiable, we know it has to be continuous. We cannot take the derivative of something that's not continuous because the point's not there. So we can't draw a tangent right here if the point is not there. If our graph comes to a sharp point, the derivative does not exist. And if our tangent is vertical, so let's say our tangent was a vertical line, the derivative doesn't exist because the derivative is the slope of that line. And that line has a slope that is undefined.